All right, in section 4.6, we're going to bring it all together. We're going to talk about how all of these derivatives relate to the original function and why they're important in the first place. So I have 3 examples in this particular section. You do not have to watch every video, but the answers will be on there and I will work through each one slowly. So feel free to skip around to as much as you want. I want you to try the problems as much as you can. So example 1, it talks about a hot air balloon rising straight up from a level field and it's being tracked by a rangefinder 500 feet from the liftoff point. At the moment that rangefinder's elevation angle is pi-fourths, notice we are in radians, the angle is increasing at a rate of 0.14 radians per minute. And it says, how fast is the balloon rising at that moment? So these types of questions show up everywhere on the AP exam. So our strategies are listed down there. So there's 7 steps. The first is to draw the picture, name all the variables and all of the constants, write down all of our additional numerical information. What are we trying to find? And then try to come up with an equation that relates all of those variables. Find the derivative with respect to time. That's where implicit differentiation is going to come into play. And then we have to evaluate to find that missing variable and answer the question. So step 1, draw that picture and name all the variables and the constants. So here we've got this hot air balloon rising straight up. And we're going to assume straight up means straight, perpendicular to the ground. So we've got this nice little right triangle. So there's my balloon. And there's my nice little basket hanging from said balloon. I would never get in a hot air balloon. You wouldn't catch me there. And you've got this dude standing out here in a field and he's holding a little rangefinder. And he is trying to determine how far away that balloon is. So here we've got some different variables. The guy is standing 500 feet from the liftoff point. That's a fixed value. It's not going to change. That x value stays put. Now this value changes for how high that particular balloon is. So I'm going to call it y just because it's my vertical component. The other thing that's changing here is as this balloon is going up, this angle is also changing. So I'm going to name that theta. So at this particular instant, we know that theta is equal to pi-fourths. That's the instant that's in question right now. We also know that the angle is increasing at a rate of, and when you see this, you know you have some sort of a rate of 0.14 radians per minute. So that's a change in theta with respect to time. Now, I do need to define my variables up here. Theta is my angle of elevation. And y represents the height of the balloon. It's important for you to identify the variables in the problem and actually tell the reader what we're actually looking at here. So we have these extra little pieces of information. I've got theta and d theta dt. And what we're trying to find, if you come back up here, it says how fast is the balloon rising? So I don't want to just know y, I want to know how fast, the change in y. So we're trying to find dy dt, the change in y with respect to t at theta equals pi-fourths. So now I look at this information. I look at step 2 and step 3, and I need to come up with an equation that relates these variables. I've got y and I've got theta. So I need to come up with an equation that relates theta to y. Because it's a right triangle, I'm going to think SOHCAHTOA. And so I've got opposite and I've got adjacent. So I'm going to use tangent. I'm going to say y equals, oops, not y equals, tangent of theta equals, sorry about that, opposite over adjacent. Now, I know I'm going to have to do a derivative because I've got these rates in here, and this equation has no rates. These are static values. So I'm going to rewrite this equation. I'm going to multiply by 500 on both sides. So I get y equals 500 tangent theta. So in order to introduce these rates into the question, I have to differentiate with respect to t. Notice there's no t's in this question at all. So this is that implicit differentiation. The derivative of y is 1 dy dt. Now 500 is just a constant, so I'm going to just put it out front. Derivative of tangent of theta is secant squared theta. But again, that doesn't have a t in it. So it's secant squared theta d theta dt. So now I've got all of these rates, and my equation relates theta, d theta dt, and dy dt, which was all of this information that I had up here. So the last step is to actually evaluate this problem and then answer the question. So my goal was to find dy dt, so of course I don't know that yet. And then we just have to plug in 500 secant squared of pi over 4 times d theta dt, which was 0.14. So go ahead and put that into your calculator. Give you a second. And when I plug it in, I end up getting 140, and this is a rate change in y with respect to t, so my units are 140 feet per minute. So in that snapshot of time, the balloon was rising at a rate of 140 feet per minute.